Introduction. A day that ended too soon. In a development that has caught the attention of scientists and timekeepers worldwide, July 10, 2025, marked the shortest day ever recorded in recent history, due to a sudden and unexpected acceleration in the Earth's rotation. The planet completed its rotation a few milliseconds quicker than the standard 24 hours, reviving serious discussions among scientists and timekeeping institutions about the possibility of introducing negative leap seconds, a measure never before implemented in human history. This phenomenon may sound trivial on the surface, but it has deep implications for everything from global timekeeping and GPS systems to international internet infrastructure. Let's dive into the scientific, technological, and philosophical layers of this unfolding story. The shortest day. What actually happened? According to data released by the International Earth Rotation and Reference Systems Service (IERS) and verified by atomic clock measurements, the Earth's rotation on July 10 was completed in 23 hours, 59 minutes, and 59.998 seconds, a full 2 milliseconds shorter than the conventional 24-hour day. While such a tiny discrepancy may seem inconsequential in daily life, for systems that depend on ultra-precise time synchronization, even milliseconds matter. Scientists refer to this phenomenon as a negative deviation in rotational length of day (LOD), and July 10's record-breaking figure was the fastest observed since precision measurements began. What causes Earth's rotation speed to change? The Earth's rotation isn't as constant as once believed. Over the past few decades, scientists have discovered that several factors can subtly affect the planet's spinning speed. 1. Core mantle interactions. Movement in Earth's liquid outer core can transfer angular momentum and speed up or slow down the planet's rotation. Some scientists believe we are now observing a shift related to core fluid dynamics. 2. Glacial rebound and climate change. As glaciers melt due to climate change, mass redistributes from the poles toward the equator, subtly changing Earth's shape and angular velocity. 3. Seismic activity. Large earthquakes can actually shift the mass of the Earth enough to slightly alter its rotation. For example, the 2004 Sumatra earthquake shortened the day by microseconds. 4. Atmospheric and oceanic currents. Seasonal wind patterns and ocean movements affect how mass is distributed around the Earth's surface, and that impacts rotation speed too. 5. Chandler wobble and polar motion. The Earth's axis wobbles slightly as it spins. This can change over time due to internal and external forces, influencing rotational speed. July 10. These anomalies seems to be part of an emerging pattern of gradual rotational acceleration over recent years, making the day shorter by tiny increments, but at a seemingly increasing pace. The role of atomic clocks in timekeeping. How do we even know the Earth rotated faster? The answer lies in atomic timekeeping, which defines the International Atomic Time (TI) and Coordinated Universal Time (UTC). These timescales are managed using an array of atomic clocks placed at various observatories around the globe. TI, a continuous timescale without leap seconds, based purely on atomic oscillation. UTC, the time you see on your smartphone or computer, adjusted using leap seconds to match the Earth's rotation. Leap seconds are usually added to account for Earth slowing down. However, a negative leap second, the removal of a second, has never been implemented. With Earth speeding up, we may now face the unprecedented task of subtracting time to realign atomic time with astronomical time. The debate over negative leap seconds. The mere concept of a negative leap second is causing heated debate among experts. Here's why. Pros. Keeps atomic time and solar time aligned, prevents drift between clocks and the actual position of the sun in the sky. Maintains long-term accuracy for civil and scientific use. Cons. Technological risks. Many digital systems are not designed to handle negative time jumps. A missing second could crash software or cause errors in database logs and network synchronization. Complex implementation. Coordinating a leap second deletion across global networks is exponentially more complex than adding one. The International Telecommunication Union (ITU) and global timekeeping authorities have long resisted implementing negative leap seconds due to these challenges. But now, pressure is building. There are real risks to not acting, said Dr. Lars Wenström, a leading geophysicist in Sweden. If the rotational acceleration continues, we may face a disconnect between the way we measure time and the reality of the cosmos. What would a negative leap second look like? A traditional leap second is added like this. 23 hours 59 minutes and 59 seconds. 23:59, 60 extra second. 0 hours 0 minutes and 0 seconds. A negative leap second would remove a second, resulting in 23 hours 59 minutes and 58 seconds. 0 hours 0 minutes and 0 seconds. The 59th second would be skipped. To most humans, the missing second might go unnoticed. But for time-critical applications such as stock trading systems, internet timestamp protocols, air traffic control, satellite-based GPS navigation, even a single second missing can cause confusion, mismatches, or dangerous errors. Potential global impact. 1. GPS accuracy. GPS satellites rely on atomic clocks and exact timing. A mismatch due to shorter days could throw off location data by several meters. 2. Financial markets. Automated trading depends on synchronized timestamps. A sudden shift in time could result in misinterpreted trades, legal disputes, or systemic risks. 3. Telecommunications. Mobile and broadband networks use synchronized timing for call routing, data transfer, and 5G networks. Even tiny time mismatches can degrade service quality. 4. Scientific research. Astronomical observations, satellite telemetry, and experimental physics all require precise timekeeping to correlate data across countries and observatories. If not addressed properly, a faster Earth could introduce new layers of uncertainty across multiple global systems. Are we headed toward a new timekeeping era? The July 10th incident is not a one-off. Scientists have noted a trend toward shorter days in recent years. In fact, 2020, 2021, and 2022 all featured multiple days that were shorter than the standard 86,400 seconds, a phenomenon not seen in prior decades. In light of this, the IERS has called for a global conference on timekeeping strategies in late 2025. Several proposals include phase out of leap seconds entirely, switching to continuous atomic time, or developing flexible time zones that drift slowly over centuries. One radical proposal suggests simply letting atomic time drift from solar time and periodically adjusting civil clocks every century, a kind of calendar correction for the modern age. Philosophical and cultural reflections. Time has always had symbolic, spiritual, and societal importance. Ancient civilizations tracked stars and seasons. Religions organize prayers by solar and lunar cycles. Now, we may be entering an age where nature no longer dictates time, but machines do. Is it time to redefine what a day is? Could we be witnessing a new Copernican revolution, where not even Earth's rotation is the center of timekeeping? Conclusion. Tick-tock, what now? The Earth's